Welcome to Study Loop.
So in this problem, we are given with a reaction of the formation of ammonia from nitrogen and hydrogen gas, and we are given the standard Kp value for this reaction, and then we are given three different mixtures of these reactants and products, and we are asked to find out whether those reaction mixtures are at equilibrium or not. And if they are not at equilibrium, we have to find out in which way the reaction need to go, whether forward or backward, to reach the equilibrium. So um, in first one, we are given the quantities are 98 atmospheric pressure, which is the partial pressure of NH3. So you're given the partial pressure of NH3 as 98 atm. Then we are given the partial pressure of nitrogen as 45 atm and the partial pressure of hydrogen as 55 atm. So these are the equilibrium partial pressure of each of the reactants and products. Now what we'll do is we'll find out the reaction quotient in terms of pressure for this reaction, and that will be basically the partial pressure of the products over the partial pressure of the reactant, and the product here is NH3, and we have to raise it power to 2 since the coefficient of NH3 in the reaction is 2. Then in the denominator we will place the reactants, so it will be partial pressure of nitrogen whose coefficient is 1 times the partial pressure of hydrogen whose coefficient is 3, and that's why we will raise the power up to 3. Now what we'll do is we'll just plug in the values. The partial pressure of ammonia at equilibrium is given as 98, so we'll square it up, and then for nitrogen it is 45 times, for hydrogen the value is 55, and we'll have to power it up to cube, and this will give us a value of 1.28 times 10 to the power minus 3. So this is um, the reaction quotient in terms of pressure for this mixture. Now we're given the value of Kp, standard Kp, as 4.5 times 10 to the power minus 5. That means this should be the value of the reaction quotient at the equilibrium. So since this value is different, that means this mixture is not at equilibrium. Now we can obviously see that this value is greater than the value of Kp, which is 4.5 times 10 to the power minus 5. So since this value is greater than um, the Kp value, that means in the reaction mixture we have greater amount of product present than we need to reach the equilibrium. That means if we want to reach the equilibrium, we need to reduce the value of Kc up to the value of Kp, and to do that, what we have to do, we have to decrease the amount of so we need to decrease the amount of the product, and we have to increase the amount or the partial pressure of the reactants. So the summary is, for this reaction mixture we need to favor the reverse reaction, or some of the ammonia need to decompose to produce some of the nitrogen and hydrogen to reach this reaction mixture into equilibrium. Now in the second one, the partial pressure of NH3 is given as 57 atm. For nitrogen it is 143 atm, and for hydrogen the partial pressure is 0. So we are said that there is no hydrogen present in the mixture. So the QP value for this will be again the ammonia's partial pressure squared up over nitrogen's partial pressure times hydrogen partial pressure whole cube. So from the mixture we can see that since there is no hydrogen present, that means the reaction has already gone into completion. So if we write the value here, since there's a 0 in the denominator, the value will be infinity. That means the reaction quotient for this mixture is infinite. And that's because since there is no hydrogen present in the mixture, that means this reaction is not in any kind of equilibrium, or the rate of the backward reaction for this one is 0. So no backward reaction or reverse reaction is going on since there is no hydrogen present in this mixture. So if we need to reach the equilibrium for this reaction, again infinity is obviously greater value than the Kp value given here. That means if we need to reach the Kp value or to reach the equilibrium, again we need to decrease the amount of the product, and we need to increase the amount of the reactants or the partial pressure of the reactants, and we can do that by forming some reactants or nitrogen and hydrogen by decomposing some of the ammonias. So for the second reaction mixture also we need to have some reverse reaction to form some reactant to reach the equilibrium. Now in part C, the values are for ammonia, the partial pressure is given as 13 atm. For nitrogen, it is given as 27 atm, and for hydrogen, it is given as 82 atm. So again, if we write down the reaction quotient in terms of pressure for this, it will be ammonia's ammonia's partial pressure squared up over nitrogen's partial pressure times hydrogen's partial pressure, which is 82 whole cube, and this will give us a value of 1.14 times 10 to the power minus 5. So this is smaller than not too small, but it's smaller than the Kp value of 4.5 times 10 to the power minus 5. So in this case, the Qp value is lower than the Kp value. That means we have greater concentration of the products, or we have greater partial pressure of the products than we have. So we have greater partial pressure for reactants than we have the partial pressure for product. That means if we need to reach the equilibrium for this reaction mixture, we need to increase the rate of the forward reaction to make some more product or to make some more ammonia by just increasing the forward reaction rate, and this way we can have some more product and we can have some less reactant, and this way we can increase the partial pressure of the product, and we can decrease the partial pressure of the reactant, and this way um, we can increase the value of the product and we can decrease the value of the reactant, and this way we can increase this value up to this value to reach the required Kp value, and this way we can reach the equilibrium.